join as we go through. So welcome to everyone for coming along. Thank you for coming along, sorry. And welcome to our last seminar of the term, which is looking at topics in seismology. So I'm co-hosting this evening. My name is Will. I'm at the University of Oxford, and I'm co-hosting with Safi, whose camera has mysteriously disappeared, but usually will wave and say hello. So the structure of the talks will be, we'll have about 15 to 20 minutes per talk, and then about 5-10 minutes for questions after each talk. And if you want to ask any questions, then do put them in the chat. And Safi will read them out at the end of each talk. I will also put a link to a feedback form in the chat, and if people want to give us any feedback about the running of the seminar or any feedback for the speakers as well, which can be done anonymously, then feel free to do that as well. We're also looking for some speakers for next term, so if you want to get involved on that side of things, and if you've got some exciting research that you want to share, then drop us a message. Again, I'll put some contacts in the chat that you guys can contact us through. And please do keep your microphones muted as well for the talk this evening. So the TETHYS seminars, just as a kind of for an idea that people that haven't come before, they're kind of to try and provide a platform for young geoscientists to present their research within a safe setting, independent of race, gender, religion, sexuality or background, and any actions or comments which may be considered discriminatory, disrespectful, or compromise the safe and inclusive nature of the seminars are forbidden during the seminar or on any comments after the seminar as well. And I won't talk for any longer, I promise. So our first speaker this evening is Savvas Marcou, who's a third-year student at Imperial College and did a research project over the summer on receiver functions, and will be talking to us about that this evening. So Savvas, if you want to share your screen and go for it.
Yep, thanks, Will. So hello, everyone. Just share my screen. Let's hope this works. PowerPoint doesn't crash. Okay.
Yeah, it's all good.
So full screen. Hope that's full screen now.
Yep.
Yep. Okay, so I'll get started. So I'll be talking today about what can HK stacking tell us about the Pacific Northwest. This was a project I did over the summer, over 6 weeks, with the soon-to-be Dr. Chris Ogden and Dr. Ian Bastow at Imperial College. Okay, so brief overview of what I'll be covering today. So why on earth do we care about the crust, and how can we learn more about the crust? The way to go is receiver functions. Talk about what receiver functions are. And I'll talk about the special method that we use to exploit receiver functions, which is called HK stacking, and the problems that that method has. And then I'll talk about a new method that we try to apply this summer from a paper from Ogden et al. And I'll tell you about the actual study that we did with the Pacific Northwest of the United States. Okay, so for the crust of the Earth, that's the upper layer of the Earth. We want to know how thick it is and its VP-VS ratio, so the ratio of the P to atmospheric velocities, which we shorten to K. Now, the value of K can be related to crustal composition. It's typically in the range of 1.7 to 2. And mafic crust has a higher K than felsic crust. Very high values of K can indicate presence of melt or fluid-absorbing gases, which we tend to see in rift settings such as in Ethiopia. Now, with the crustal thickness, why is it important? Now we can relate the crustal thickness to all sorts of things, like does thick crust relate with high topography? What is supporting topography? We can do all sorts of investigations with that. But first, we need to get the information. So how do we get the information? As I'm sure you all know, we record earthquakes at seismic stations and we get wiggles out of them, seismograms. This is a recording from the BGS. It's probably in Scotland, a station in Scotland from a distant earthquake. So what the wiggles mean, they're not just what the earthquake does, they're a combination of things. So if we take it in the time domain, the seismogram is a time series. It actually represents the convolution of a number of things. So the STF, the source time function, is what the actual earthquake does. Then we've got the path effects. So what happens to the wave as it travels through the Earth, how the Earth alters that wave. Then we've got the instrument response, because our instrument is a physical instrument. It cannot exactly replicate the response. It's got a response of its own. So that's kind of alters the signal we get from the earthquake. And finally, we get the receiver function. Receiver function is kind of the time series of describing the Earth response to the wave beneath the station. So it's immediately below the station. Now, we usually get 3 component data from our stations. And what we tend to do is rotate this 3 component system, which is vertical, north, south, and east, west, so vertical in the horizontal plane, rotate it into a new coordinate system, vertical, radial, and transverse, so ZRT system. Radial direction actually means we're rotating the component of the seismogram that we're recording in the direction that is the path between the station and the earthquake. So if we were pointing along the radial direction, we would be pointing from our station directly towards our source, directly towards our earthquake. As I said, the receiver function is a time series, which is hidden in here, expressing the earth response beneath the station. So how do we get it? It's a mathematical operation, officially called a deconvolution. We deconvolve the radial from the vertical component to get a radial receiver function. This is just a division in the frequency domain. And it will make sense why we do this with the radial and the vertical component. Now, how does a receiver function look like? We go from seismograms in the 3 components, we rotate them. We go to wiggles in a slightly rotated coordinate system, we do the division radial by vertical, and we get the receiver function. So the first arrival on the receiver function, the highest amplitude one will always be the direct P wave, the first arrival, and then the rest of the stuff in the receiver function, the rest of the wiggles will be the earth response. Now, how does that earth response actually get produced? Now, P waves that arrive from the earthquake towards our station, they will cross the moho. The moho is the crust mantle boundary. It's a sharp velocity contrast. It's a compositional boundary between the mantle rocks and the crustal rocks on top. So, as I'm sure anyone who's done a seismic reflection course will know, if we get such waves crossing a discontinuity and interface, we get P to S conversions. We convert P waves into S waves. Now we've got a number of converted phases which get trapped in the crust and they start reverberating in the crust. You get lots of reflections. Just a note on notation here. So we get things which are capital letters. There are waves which are coming downwards and bending upwards. And then the lowercase letters represent stuff which is going up. So a PS is basically a wave which is coming in as a P wave, gets converted to an S wave at the moho, and goes up and gets detected at our station. So we've got 3 characteristic phases, which their arrivals at our station depend on the crustal thickness H and the PVS ratio. We have equations to calculate these arrival times if we know H and K, which is something that we're looking for, of course. Now, to determine the crustal thickness and K from receiver functions, we know that they trade off very strongly. So arrivals which are arriving later may be caused by thicker crust or a crust which is slow. We can't distinguish between them. So these 2 people, Zhu and Kanamori, who gave us the magnitude scale, came up with this method, HK stacking. So what we do is basically take lots and lots of receiver functions, lots and lots of earthquakes. We produce receiver functions from the seismograms for those earthquakes, and we stack them. We align them in time, and we add them together. Now, stacking suppresses noise. It enhances our signal. So we're going to bring out very nicely those arrivals we were talking about on the previous slide. And we do a grid search in the HK parameter space. So we put plausible values for H and K, and we do a grid search. How do we do our grid search? Our aim is to maximize this function here, which looks a bit horrible. What it actually does is it searches this space to find the right times at which the PS, the PPPS, and PPSS or PSPS phase arrive. So if we're getting the right values of H and K, then we're going to get the right times. We're going to sample the receiver function at the right time when the amplitudes will be positive, positive, and negative. And this function here will be a maximum. So we're going to get a nice bullseye in our parameter search, and we're actually read off the graph to read H and K. Now, Zhu and Kanamori made a fundamental assumption, though, that the crust is simple, that the moho is sharp, and it will be the sharpest velocity contrast our wave will encounter. So it will produce the highest amplitude arrivals. So what we will find from this grid search is actually the values which are produced by the P2S conversions from the MOHO. Now, HK stacking runs into trouble because the Earth, as we all know, is not perfect, it's not simple. So the MOHO may not be sharp, it may be gradational, or you may have other sharp velocity contrasts on top of the MOHO. So in the case, for example, where we have fixed sedimentary basins, that will give a strong contrast with the crystalline crust lying below it, or in the case of a large igneous province, which may be overlain by sediments, we may have more contrasts. So sediments and basalts really make it hard to get those really sharp high amplitude arrivals we would expect from a simple MOHO. So our receiver function becomes really messy and HK stacking doesn't really work. Now, the way to get around this is, so this group of investigators, in 2019, they came up with a method to correct HK stacking. So in typical HK stacking, you select a VP, P-wave velocity, you select your stacking weights, which you use to judge the importance of each phase in your receiver function, and your frequencies, you just do it in HK stacking, you get a result, but you don't know how good that result is. Now, Ogden et al., they allowed parameters to vary freely. So they did their stacking for a range of VP velocities, a range of stacking weights, a range of frequencies, and they do statistical analysis called cluster analysis. That's all explained in their paper. And they look for clusters of results. Now, a sharp MOHO gives a very, very tight cluster. A MOHO which is not sharp and it has other discontinuities on top of it gives a rubbish result with lots and lots of clusters. Now, the real innovation in their method is that they implement frequency limiting analysis. So in typical HK stacking, we would be doing the work across all frequencies. Ogden et al., they turn down the frequency. So they deliberately turn down the resolution of the method so that, as we all know, if we turn down the frequency, the wavelength will increase and our vertical resolution will become worse. So we become less sensitive to thin layers. So in that way, we can sharpen the MOHO if the overlying crust is simple. And by implementing frequency limiting analysis, we can actually start to get sharper arrivals, which will improve our result, hopefully. So they tested it with some synthetic data, and they found that with a 5 kilometer thick MOHO, you can resolve it at all frequencies. If it's 5 to 13 kilometers thick, then by limiting the frequency, you've got a chance of seeing the MOHO and getting a good result. If it's thicker than 14 kilometers, so you've got a thick high velocity layer at the bottom of the crust, which is very thick, you've got no chance basically using this method. So they judge the reliability of their solution based on a set of 10 criteria. To be absolutely confident that the result is good, we needed to pass more than 9 criteria. The criteria is listed here. It's a bit complicated, but it's basically about having a result which is logical within the parameter space, which has small errors, so small standard deviation, small errors, the average. So then we define also a series of metrics to judge how good our result is. We define something called the amplitude correlation estimate, which compares the amplitude of the first phase in the receiver function after the direct P wave, the PS, to the receiver function's root mean square amplitude. So if the MOHO is sharp, then ACE should be quite high because PS will be high amplitude. CCC is just a cross correlation coefficient. It tests for noise and whether we have azimuthal variation. So depending on the direction from which the earthquake is coming from, whether we get a different timing of arrivals of the receiver function. And then also we calculate the signal to noise ratio, which basically compares the PS amplitude to the noise we get before the first break of energy. So that should also be higher for a sharper MOHO. Now, in my study, I chose to focus on the Pacific Northwest to apply this method to the Pacific Northwest because it's got a perfect recipe for the HK method to fail. Now, we've got subduction. We've got a plate, Juan de Fuca plate coming from the west. Now, subduction will give you 2 MOHOs, So that will fail. That will cause the method to fail. We've got flat basalts. If we've got sediments on top of them, then we've got sharp velocity contrasts above the moho. So that makes the crust not simple. And we've got a plume down here, Yellowstone plume. We've got a series of calderas which get older this way as the plate was moving over them this way. And we know that plumes, it's been said in the literature that plumes are associated with a thick underplated layer. So a seal of high velocity material gets injected into the lower crust, and that makes the moho not very sharp. So we can test for a series of things here. And also we've got the Rocky Mountains, and being a big mountain range, they will have significant sedimentary thicknesses on the edge. So in the form of foreland basins. As the mountain settles down, it creates bowls which can collect sediment. So that can also give us discontinuities. Now, the data we're using is from the transportable array, which is a big collection of temporary stations across the United States. We use data from 4 years. We used quite large earthquakes to make sure we get high amplitudes. And we did some quality control to see if the seismograms were noisy and if the resulting receiver functions were noisy, because they are useless if they're noisy. Now, and then we go on to the results. First, we need to look at the data that we have. We need to have enough receiver functions to get a good result per station. We're saying that less than 5 receiver functions is not good. So we can see that on the coast, we get lots of noise. So we don't have very good data availability. It gets much better as we progress inland. Interestingly enough, out here in the Wyoming Craton, it's quite noisy, and we get very few receiver functions which are good enough to do the analysis. Okay, so going on to the results. If we did simple HK stacking, we would have had a happy collection of crustal thicknesses and the PVS ratios across this region. We would have started interpreting this and saying what it means for the topography and the composition. But this method enables us to do better, enables us to think about the reliability of our results. If we think about the reliability of the results, so the stations which are passing more than 9 criteria, we've got just 16 of them, of the big collection that we had initially. So we see that the stations which are quite successful in this area of crystalline rocks in the northern part of the Washington state, in the place called the Northern Cascades, it was like a predecessor to the Cascade volcanic range. We see that it's got normal continental crust, 35 kilometers thick, and a felsic composition, which agrees with what we get from the geology. Also, the Idaho batholith down here, big granitic batholith seen from geology. We see that it has thickened crust and a felsic composition. And then we'll see something about its moho as well. Now, I keep talking about doing the analysis on a station by station basis and all those criteria. So what the analysis looks like for a good station, which passed all 10 criteria, so you can see 10 green lights. We see something like a very good bullseye. We see a tight cluster, and we see that at T1, the predicted T1 that we get from this bullseye, we're indeed sampling a high peak. Same with T2 and same with T3. And we see that the station doesn't have any variation if we consider azimuths. For a bad station, you can see that this is very messy. The result is on the edge of the parameter space, lots of clusters. We can't really find a good one. And then T1, T2, and T3 are not clearly sampling a single peak of the receiver functions. Now, we said that the Ogden method also considers frequency limiting analysis, and we also applied this to this area. So we did find that it makes things better. Now, on the left here, we've got the results at 2 Hertz, so the highest possible frequency. We're seeing the most of the layers, which are quite thin. And then we go to the best result after carrying out our frequency limiting analysis. And what immediately stands out, apart from the improvement up here in the Northern Cascades, is that we have quite a lot of improvement down here in the Snake River Plain, which is basically the track left by the migration of the plate over the Yellowstone hotspot. So we can infer from this that indeed what was being said in the literature about an underplate being present, which made the moho gradational, is probably true. And the Ogden method gives us a fighting chance at being able to get a good crustal thickness for the Snake River plate, because we go from the red, which is not trustworthy, to the yellow, which is potentially trustworthy. We're passing more criteria. Now we can see here another plot, which is all the successful stations, those 16 stations. We see at what frequency are we getting them to be successful. Now the squares are those stations which are successful at all frequencies, so we didn't need to do anything to them. The circles are stations where we needed to turn down the frequency. So one result which stands out is that we needed to turn down the frequency to make the result reliable for the Idaho batholith. So probably that's another region where we have something like a gradational moho. It's probably not 5 kilometers. We weren't able to resolve it at all frequencies. It's between 5 and 13, which are the resolution limits of our method. And then we come back to those three metrics, ACE, SNR, and CCC. And we're going to do a second chance check on what we were saying about the moho not being sharp in certain regions. I was talking about the Snake River Plain down here, and we were saying that the results probably showed that there was a gradational moho down here. The amplitude correlation estimate, which remember tells us about the relation of the first arrival after the P wave in the receiver function, is quite low in the Snake River Plain. So it's an indication that we've got a gradational non-sharp moho down here. Same with the signal to noise ratio. The PS amplitudes appear to be quite low. Where we've got lots of success up here in the Northern Cascades, we get high ACE and a high signal to noise ratio. And same thing for the high lava plains, which is another area with potentially a gradational moho according to the literature. So in summary, the HK stacking function method is a way we can get crustal properties. It can face problems if the crust is not simple, and there are lots of regions on the Earth where the crust is not simple. This paper, Ogden et al., offers us a way out, a way to test the reliability of our results, and it is illustrated by the case of the Pacific Northwest. We get support for the presence of an underplate in the Snake River Plain. We need to ask the question there, and this is far beyond this study, is that how plumes work? Do they inject an underplate in the lower crust? The best results are in an area of the older crust in the Northern Cascades, probably simple. The Idaho batholith also seems to have an underplate, and this point is the takeaway message. Turning down the frequency improves the reliability of our HK results. So this was it from me. I think I'm on time, and I'm happy to take your questions. Thank you very much for listening.
Thanks for that. I'm sure you all know the drill now. If you put the questions in the chat, I'll read them out.
So I guess whilst we wait for questions, as per usual, I will ask my obligatory question, which I always seem to have. I was wondering with so it's quite a dense array, the US array that you're using, and even with those kind of number of stations, you seem to have to eliminate quite a few of them related to, I'm assuming kind of the noise down the coast is related to oceans and things like that. So what's the kind of scope of applicability for other places in the world for how feasible is it to do in other areas where, for example, the arrays aren't as dense, or are you just limited to continental interiors, for example?
By principle, you're limited to continental interiors because that's where you can have the most dense seismic deployments. Now, the Basta seismology group I was working with is planning to apply this method to the whole of the United States to see how well it works, because we've got the TA array already in place, the data is already in place. But essentially, you get a result for each and every one of your stations. So the more stations you have, the more results you're getting. The denser the array you're deploying, maybe you can use some techniques like interpolation to find how the moho is dipping, how if you've got topography on the moho and stuff like that. But essentially you get one result per station. So the more stations, the better for this result.
Okay, so it doesn't look like there's any questions in the chat at the moment. So I think what we'll do is, just in the essence of time, as per, we'll move on to our second speaker. But if you do have any more questions for Savvas, then drop them in the chat, and we'll definitely have some time at the end to put them in there then and to ask them then. So our second speaker is Rebecca Colquhoun, who is at the University of Oxford, also again at the best college in Oxford, and does seismology, so I'm very biased in every aspect. But so Rebecca did her master's under Professor Jess Hawthorne at Oxford, and is now continuing her research with her PhD. So Rebecca, if you want to give us a talk, that'd be brilliant.
I couldn't work out how to unmute once I was in presentation mode, but there we go. So as Will said, I'm Rebecca, and I'm going to talk to you about my master's, which was about how we can use foreshocks of earthquakes to tell us about the processes of nucleation. And so just to start with saying a bit about me, so I did my undergrad in earth sciences, and Will says I'm at the best college. I did my master's at Worcester, but I've now moved to what Will would describe as the best college at UNIV for my DPhil, where I'm looking at something related but different in earthquakes, which is I'm looking at how we can, at what point we can distinguish earthquake magnitudes like during earthquake rupture. And so that leads me on to, let's start with an earthquakes 101, which I think most of you will already have had, partly through Savvas's talk and partly because there aren't any first years, I don't think. But we have earthquakes, and hopefully everybody's heard of those, and you have foreshocks and aftershocks of earthquakes, which are the events that happen before and after, obviously. But I've carefully not put a time scale on here. And so normally when you think of like a foreshock, you might think of the Christchurch earthquake in New Zealand that was technically a foreshock, and that was a large magnitude and it was quite a long time beforehand. And so for this, you need to get rid of that as a notion sort of thing. I'm talking about tiny events like magnitude 1 or 2 maybe, that happen in the half an hour before and after an event, depending if they're a foreshock or an aftershock. And so we also then, as Savvas said, we have seismometers, and I just use them in their normal orientation of like north, south, east, west, and vertical. And those have incorporated different aspects that, such as the source time function and like effects of the path. And those are what I like rely on in my method. And so earthquakes don't like go from 0 to hero straight away. They begin slowly in this process called nucleation, which is when they go from like having a 0 slip speed to approaching seismic velocity. And so the slow phase where they're like accelerating before ruptures completely occurred is called seismic nucleation. And so before the seismic velocities are reached, so, deformation is by definition aseismic, and that means that we can't detect it at seismometers. But sometimes we get these like little patches where we reach seismic velocities in foreshocks. And so I'm hoping to use those to understand earthquake nucleation better. And then the final sort of introductory thing is that when we have an earthquake, which is like this black dot here, then that results in a stress drop region around the epicenter, which is proportional to the magnitude of the earthquake. And then outside of this, there's a region of stress increase, which I've shown here in orange. And so there's a couple of different models of earthquake nucleation. And the main like distinguishing factor between them is whether external processes have to be involved or whether the fault can just like do it on its own and earthquakes trigger earthquakes. And so the first model is that there are some external processes involved. And so what happens is there's some process happening in this gray region, and that's that moves along, and in doing so, it increases the shear stress in the white region and decreases it in the grey. And so this process might be some aseismic slip, or it could be changes in pore pressure, changing the effective normal stress. And so if you imagine the front of the external thing moving across, then that means that we trigger earthquakes just ahead of it. And this means that our earthquakes are going to move across the fault in time. On the other hand, we might not need external processes at all. And so the second model occurs when a previous earthquake provides the trigger for the next earthquake through temporary stress changes or through permanent stress transfer. And so in that case, then we get our first earthquake, and that's got this stress, it's got a stress drop region and then a stress increase. And then that triggers another earthquake because it's increased the stress over here. And then this earthquake has in turn changed the stress. And so that's triggered an earthquake here. And so they're all triggering each other through stress changes, but we're jumping all over the fault. And so this process is often called stochastic nucleation, and it's got really well-defined equations which describe the seismicity rate with time from the main shock. And so those equations are called Amori's law. And so this says that the number of foreshocks or the number of earthquakes with time from an event is proportional to about 1/t. And so we've got these other things. So we've got these constants and we've got productivity, which there's a lot of debate about what the productivity is. Some people say it's 1, some people say it depends, but it's between like 0.7 and 1.3 kind of thing. And so this means that through time, if we looked at the number of events with time from the main shock, then we expect something that's going to be about like a 1/x curve. And so that's like all the background. So now what did I actually do? Well, so I looked on the North Island of New Zealand on the Hikurangi subduction zone. And I've chosen the Hikurangi subduction zone because we know that there's some like pore fluid pressure things going on, and there's a lot of work in that. And we also know that there were aseismics or slow slip events, which happened in like the time frame I'm looking in. And so basically this is our best chance of implicating external processes in nucleation, because if we look somewhere that didn't have any like pore fluid pressure changes or any aseismic stuff, then we can't say that they did anything because they're simply not there. Whereas here there are these processes, and so if they don't seem to have an effect, then that means that we can say better that they're just like not involved. And so this is the subduction zone, and the Pacific plate is subducting under the Australian plate. And so the slow slip events that I mentioned earlier happened in like 2010 and 2011. And so that's sort of smack bang in the middle of my data, because I looked at earthquakes I tried to look at earthquakes between 2000 and the start of 2020, but it turns out that they didn't like quite have the technology in place at the time. And so I did from 2005 to 2020. And I looked at about 2000 earthquakes, which there's a dot for each of them here, and like the dot size is the magnitude, and then they're like changing in depth. So you can really nicely see the subduction of the plate. But and I used the New Zealand seismometer network, which ended up using data from 8 different stations. And so I took this data and I said, oh, well, only use seismometers within like 4 degrees of the main shock, just because the data quality gets less good the further away you go, and the more stuff that could go on. And like quality of data is like quite a key thing for me. And so I then accurately determined the time that the earthquake waves arrived at each station, because helpfully a lot of the data wasn't picked, so it didn't actually say when the earthquake arrived. And then I cut out a template event, which was like 2 seconds before and after the pick that I'd created. And so this is my template. And then I took that template and I looked for time windows across the whole like half an hour before and after record to look where the record was similar to the template in the frequency domain. And so this is something called phase coherence, and I'm not gonna go into it in depth, but I'm happy to if somebody like wants to ask later. But graphically what I'm doing is this is my template in sort of pinkish color, which hopefully you can see. And then I've taken that template and I've looked at this time half an hour before, and through convolution, I've said, is this similar? And the answer is no. And so that means that my phase coherence is really low. And so then I move my window across slightly and I say, well, is it a match now? And the answer is still no. And so you keep going all the way through. And now here, for the purposes of illustration, this is a synthetic foreshock, which is an exact copy of the start of the main shock that I've just like shoved in at a random time. And so at this point, there's like no similarity. So the phase coherence is low, still no. Oh, wow. Now it's really similar, which I'm glad it is because it's the same earthquake. That means that we get a big peak in our phase coherence. And then after that foreshock, our similarity goes back down. And so our phase coherence goes back down to nearly zero. And so this is great. On this record, we can see really well. We can say, oh, here's the peak, and this is therefore a foreshock. Let's say that's a foreshock. But the real data looks something a bit more like this. And so it's easy to find the main shock, and it's a bit less easy to say whether any of these like peaks are foreshocks or not. So I had to require statistics, which was a bit of a challenge for me. But basically I've said, oh, well, is the deviation from the average phase coherence significant at 2, 3, and 4 standard deviations? And so that means that I've come up with a record then that says like, these are all the times that there is an event. And so then I've plotted that with time. So these are the detections on the y-axis, and then this is time relative to the main shock. And so you can say, oh, well, there's about the same number of detections all the way. That's like our background seismicity. And then maybe you can say something's going on just before the main shock, but what you can really see is that there's something going on after the main shock. It doesn't just decrease suddenly. And it looks a bit like that 1/x curve that we saw before. And so let's zoom in. So this is a much less pretty figure, but the concept remains the same. And the reason that the y-axis like numbers have changed is because I've changed resolution from 10 seconds to 1 second. But so there's a tiny bit of an increase here. There's an artificial widening of the peak because of the method. And then there's a really clear gradual decrease. And so this is great, but we've not quite got the right number of events. And so as well as having that Amori law that says what it should look like through time, stochastic nucleation also says that there should be a foreshock to aftershock ratio of about 0.134. Whereas my foreshock to aftershock ratio, which is just by dividing the total number of events before with the total number of events after, is 0.047. And so in doing that calculation, I've assumed that all the detections are because of earthquakes. So there's no false detections, and that each earthquake results in a single value being elevated. And so those might not be right, but they should affect the foreshocks and the aftershocks equally. And I've also got a much better resolution than the people that came up with this number, but also that should affect the foreshocks and the aftershocks equally. And so this foreshock to aftershock ratio suggests that stochastic nucleation isn't true, because why is this number so low, and why is there like a change between foreshocks and aftershocks? And so if we go back to looking at foreshocks and aftershocks through time, we can, so in this is very similar figure, but this like pink shading is the number of aftershocks, and this blue shading is the foreshocks. And then I fitted Amori curves, which are these like 3 curves here. And so you can see that accepting the first point, which is back due towards that because of that peak widening like thing, you can see that we can do a reasonable job of fitting these with Amori curves, but you can't fit the foreshocks with the same Amori curve as the aftershocks. And so that just doesn't make sense, because you can't suddenly, if your like fault is just chilling on its own, it's not suddenly going to completely change its parameters because of an earthquake. And so we've got to, we can't, whilst we can say that there's like it seems to be a stochastic progression through time, there's a massive change between the foreshocks and the aftershocks. And so which is it? Well, our foreshock to aftershock ratio was too low for stochastic nucleation, but we see a progression through time that's a bit stochastic looking. And so if we say aftershocks are explained stochastically, then how are we going to explain the reduced numbers of foreshocks but keep them being that progression through time? And so this is why I think we need external processes. And so before, something I didn't tell you was that I like came up with a load of hypothesis tests right at the beginning, and one of them, and so I like said, oh well, how will the number of foreshocks differ between pore fluid, aseismic slip, and stochastic nucleation? And then and I also looked at various other things like how will it progress over the fault? The issue is that the pore fluid and the aseismic slip affect foreshock numbers in the same way, and so I still can't really distinguish them. But if we sit down and we just think more geologically about this, the subduction zone underwent several episodes of slow slip, but these were episodic and they weren't over the whole like 15 years of data. And so therefore you wouldn't expect them to affect all of the earthquakes, and so you also wouldn't expect the numbers to be changed so much. And so I'm favouring the involvement of high pore fluid pressure to reduce the available driving stresses and therefore influence nucleation. And so I hope that I've shown that external processes have to be involved in some way in nucleation of earthquakes. What I've not shown is whether these processes are actually involved in nucleation. So they're actually involved in the triggering of each earthquake, or if they're just altering the conditions on the fault that stochastic nucleation is occurring in. And so to do that, what I need to do next is I need to look at the spatial relationships of foreshocks, mainshocks, and aftershocks on the fault planes to understand how stress is being transferred between them. And hopefully then I'll be able to say whether they're moving linearly across the fault or not, and hopefully better contain what's going on. So thanks very much.
Thanks for that, Rebecca. Yeah, once again, put any questions in the chat.
So I have a really quick one, which I think is just gonna be a really, really simple one, like almost like a yes or no. But when you were showing your template that you were using for the phase coherence, I think it was probably maybe just because of the longevity of the time axis, but it looked almost like a delta function as such. It was quite was there actually some shape to it? Well, kind of, does that make sense? Or was it just very much a peak?
Oh, so it's like
if you zoomed in, would it?
So you mean if I zoomed in on like this?
Yes. On yeah, the template you're using, sorry.
Yeah, there is a shape to it.
Okay.
It's just that like it's like this, I've made it so the beginning of the earthquake I get like 2 seconds before the pick, which is really like 1 second before stuff that you like sort of see is going on. And so on a scale like this, it's a delta function.
Sure. Okay, cool. Thank you.
Nikki has asked, is there an earthquake sequence / location where you think you can spatially resolve it?
So hopefully I can do it on these earthquakes. I just haven't. But yeah, so it's pretty high data quality, and so at the moment I'm looking for sequences. So I'm looking for where there's like multiple foreshocks in like say a 10-second window, and hopefully then I'm going to be able to look at those in detail, and I'm going to be able to say, oh, these are next to each other or not. And so that's like very ongoing. I was doing it whilst I was supposed to be in class today.
I have one more question as well, which is, so you were saying about the potential for pore fluid pressure being a cause in this kind of catalogue that you've looked at. And I'm wondering if this is something that you'd, do you think that could be something that's just an artifact of the area that you're looking at in New Zealand, and you need to actually kind of sample a load of different areas around the world, or do you think it's more likely to be a common feature?
Yeah, so I'm looking somewhere that we know has it going on. And so I think if I was looking at somewhere that wasn't a subduction zone, for instance, then I'd be much less likely to be saying, oh, it's pore fluid pressures. But I also, so the ideal thing to do would be to look at loads of different places. But I also, there's been some past work looking at this. There was some people did it in Alaska, and some people did it in like Turkey, and they both found really different conclusions. But I think what they forgot is that it might not be the same everywhere. And so I might be able to say, oh, in New Zealand, it's because of pore fluid pressures. And there's no reason that it has to be the same in Turkey. Earthquakes can be individuals if they want.
Okay.
Tamsin has asked, are there faults where pore fluids or aseismic slip aren't factors, but earthquakes still take place? And how likely is it that both of the mechanisms, stochastic or external factors, are important in different places?
I'm not sure if there's anywhere that conclusively doesn't have slow slip. There might be, I don't really know. But what was the second part of the question?
How likely is it that both of the mechanisms, stochastic or external factors, are important in different places?
I think it's quite likely. I'm quite in that camp. Other people would say no, it's going to be one or the other, and quite what the external process is, let's say, is going to be different, but it's always going to be involved. But I think that it's quite likely that earthquakes could be like happily nucleating stochastically, and then like if an external process comes along, the external process sort of swamps stochastic nucleation, and so we see something that's influenced by external processes. But if we like could switch off the external process, then it would go back to merrily stochastically nucleating. But it's quite debated, I think. It's all debated. It's less debated, however, than my PhD proposal, which is like really debated.
Cool. Okay, so I think if there are any more questions, pop them in the chat now, and I'm sure we can ask them. I'm just going to put I realised that I kind of spoke on earlier, saying that I'd put a feedback